Hey everybody, sorry I'm a bit late. Just finishing up an exam. Right. Okay, let me go ahead and share my screen and we can get started today. Okay. All right, so how's everyone doing today?
Good.
Pretty good.
Good. Exams done. Good. So I haven't looked at the exam yet. So I probably plan on starting that probably early next week. But I should have them graded before our next class meeting on Tuesday. Nice. Everyone's done with their first round of exams, so that's good. Yeah. So so if you're just coming in, I was just saying that the exams I'll probably grade before next Tuesday, probably on Monday, because I do have something I need to take care of for the department tomorrow. But you'll know your scores by Tuesday. Okay. Um, Another announcement I want to make is that the final project specs. We talked about it I think a couple weeks ago, but I think only about half the class have chosen a model at this point. And so if you haven't chosen a model yet, and you haven't let me know which image data that you want to use, please go ahead and do that. I think so far everyone on the sign up sheet I've gotten to so far. Yes. So I just sent Carlos and Brianna their image data today. Oops, that's my email. And so if you haven't told me what model you're doing yet, you can use the sign up sheet, or if you want to just email me, then I can, and that's fine too. And then I'll upload your image data and your and the pictures of your model onto Dropbox, and I'll send you the Dropbox link because unfortunately the files are a little bit too big to send by email directly. Oh, yeah. So if you and so the model that you choose, it's not a binding contract too. And so if you end up wanting to do a different model, that's fine with me. Just let me know. But just be aware that when you change, then that's last time to work on the model. And so if you and so I would definitely encourage you guys, if you've gotten your image data, go ahead and start working on the project, just to get a sense of how complicated it's going to be, because I know a lot of people have chosen aorta models, and I think aorta models are really good for this project. But some of you did choose some more challenging models than that too. So I think the challenging models are fine. It's just kind of going to be a matter of how much time you have to dedicate to building that model. Okay. But fortunately, building the model is going to be the most time consuming part. And so once you've constructed that, or at least, you have most of the vessels that you've kind of checked it with me, then you can move on to the simulation from there. Okay. Um, and so, make sure you choose your models, and then I'll send out another batch of image data either probably tonight or probably tomorrow. Okay. All right. And so today, I know in the schedule today, I had planned our second SimVascular workshop on CFD simulations. But, I just realized that, probably a lot of you guys have never even ran a CFD simulation before. So actually what I did was I put together just a quick set of lecture slides on, what is CFD and just what are the general steps to running a CFD. I thought that would be useful to talk about, so that a lot of this information is you can transfer to other CFD programs. It'll also be kind of a nice precursor to before actually working with the CFD solver within SimVascular. Okay. All right. All right. Question. So did you have a soft deadline for the model? There's no deadline for selecting one, but then April 23rd is a deadline, because that's when I want you guys to be done with the modeling of the geometry. Okay. And so I would say at least give yourself, since it's going to be your first time working with a new set of image data, give yourself at least a couple weeks, to work on the model, 2 or 3 weeks. And so by April 1st, I would say that's probably the best time to select the model by. But the sooner the better, of course, because it's going to take a while, and I anticipate probably a lot of a lot of you guys will be coming to office hours to ask for help as well, because medical image data, even though I know we did the tutorial together, but the first time you look at a new set of medical image data, it's really disorienting at first, because you're not really sure what to look out for, and you're not really sure how to really start. And so definitely give yourself the time to start the geometry, because it's going to take a bit of time. Okay. And so actually, before we talk about, intro to CFD, I did want to finish up our lecture notes on medical devices. So I think we left off talking about artificial heart valves. And so I do want to finish that up. just because there is some really interesting stuff at the rest of in the rest of the selection notes, and then we'll talk about intro to CFD, and then next Tuesday, we'll talk about how to actually set up a CFD simulation within Vascular, and I'll also show you how to connect to the supercomputer as well. Okay. Okay, so that's the plan for today. So are there any questions I can answer before we get started? Oh, nice. Yeah, yeah. So Star CCM is definitely a popular one as well. I think that's used it for a lot of aerospace applications. I haven't used it personally, but I have heard the name come up quite a bit. Okay, so let's go ahead and continue on. Okay. And so this is the end of our lecture notes on cardiovascular diseases and medical devices. And so we finished covering actually most of it last time, but there's a little bit still that I wanted to cover on, artificial heart valves and actually whatever comes after this. I kind of forgot. And so we'll see when we get there. But first, let's talk about heart valves. And so just to kind of refresh your memory, heart valves or just valves in general in your cardiovascular system, they have kind of one primary function, and that's just to make sure that blood only flows in one direction, right? And so ideally, flow should go forward through the valve, and then, the valve will close and then prevent flow from coming back, through the valve. Oh, question. So do I have an opinion on using ANSYS for CFD? I think it's fine. I think it's good. A lot of people use ANSYS for research, actually. The only caveat is that you probably have to purchase the commercial version for ANSYS, because the free student version of ANSYS just doesn't give you enough elements to actually run like an accurate simulation. And the thing with CFD is that you need really good mesh density in order to actually run something that's accurate. And so if you can get your hands on a commercial license for ANSYS, I think it's great. But the student version of ANSYS, I think, just doesn't give you enough firepower to really do anything useful. Yep. Okay. And so, these valves are actually passive devices, and so it's not really like an active thing. It's not like a muscle that your body is like opening and closing. It's really just passive. And so basically, when you have a pressure gradient through the valve, and it's going from high pressure to low pressure, flow is going to go through. Then once that pressure difference, reverses, then the valve kind of shuts off on its own. Okay. And the way it does this is that, these valves are basically made of a very flexible cell membrane, and we typically call them leaflets just because they look like, a lot of them actually look like leaves, and they're kind of, thin and flexible like a maple leaf. Okay. Okay. But even though they're just passive structures in your system, primarily we're concerned mostly with the valves inside your heart. They can get disease just like any other part of your cardiovascular system, right? And so typically there are two types of diseases that valves can undergo. And so the first type of disease is called stenotic valve disease. And so what this means is that the valve becomes very stiff. The leaflets become very stiff, right? Because normally, these valves depend on these leaflets being very flexible, like a leaf, going through the wind, okay, in order to function properly. But what can happen sometimes that, just due to aging or due to some other factors, that these valves just get really, these leaflets get really stiff. And so whereas they're supposed to open, very naturally and very easily, they kind of like creak open like that. And, they're not able to do their job. And so when that happens, then the valve doesn't open all the way, and it doesn't allow as much blood flow as it should be. Okay. And so that ends up putting a lot of extra strain on your heart, because your heart has to basically push the blood through a much smaller space than if the valve were totally open. Okay. And so that's stenotic valve disease. And so the other type of valve disease that happens often is called regurgitant valve disease. And so what this means is that the valve often doesn't close all the way, or there might be some abnormality in how the valve closes. And so once the valve closes, normally it shouldn't allow any flow to come back, but a regurgitant valve will have holes and flow will start to leak kind of backwards. And this is a big issue, because this will basically make it so that your heart is not working at maximum efficiency. Right? Because the big reason why these valves close is to basically make sure that the heart can function properly. And so one example for this is like, for the ventricle, your left ventricle, which pumps heart to the rest of your body, it relies on the fact that the valve on the backside of the ventricle is going to be closed. And so when it squeezes, it squeezes really hard, all that blood will go to the rest of your body and none of it goes back, backwards in the heart. Because if you have some flow that's going backwards, that's really inefficient. And so that's really going to affect how the heart behaves. All right. And so, when these valves get diseased, you have to go in and treat them just like any other cardiovascular disease. And the thing is, just based on the cells that line these valve leaflets, it's really difficult for the body to repair these valves on their own. And so any kind of really serious valve disease like a stenotic valve or regurgitant valve, doctors have to go in and actually replace that valve with an artificial one. Our question: so what are the valves made of? Is it cartilage-like? Actually, yeah, that's a great question. I'm not sure. I don't think it's not cartilage. I don't think it is actually like endothelial cells, but I'm actually not sure about how exactly they are different from like your blood vessel wall cells. But I don't think that they're cartilage because they are very flexible, and if you kind of see them in action, you'd kind of see like they look very flimsy when they're kind of in action, but they're flimsy, but they make like an airtight seal. And so I know that their material is different from cartilage, but what they're actually made of is I'm not exactly sure. Yeah. No, there's no muscle, so they're completely passive structures, and so the body can't actually like contract them or control them really. So they're really just passive structures inside your heart. Yeah. Oops. All right. Okay. All right. And so here's a couple pictures of some artificial valves that that can work. And actually, Edwards Life Science, which is the one that's the big biotech company that's down in Irvine, a lot of their work is actually in artificial valves. And so I remember I visited sometime last year, pre-pandemic, and they actually have like a gallery of like a lot of the heart valves that they've developed over the years. So it's really fascinating. And so if you're into valves and you want to work at Edwards, this is a lot of groups there are dedicated to these kinds of valves. All right. Oh, 3D printed valves. Oh yeah. Oh, I'm sure that's a big area of research as well. That's definitely sounds really interesting. Yeah. Nice. How big are these valves? Yeah, it's a good question actually. I'm not sure about their exact diameter, but they're tiny. So I mean, I'd say they're definitely smaller than a dime for sure. Yeah. Oh, nice. Yeah, 3D printing is definitely a big area for this as well. Yeah. All right, so valve. So if you do make an artificial replacement valves, it kind of has to have a few qualities that make it really good, right? And so first of all, they have to be extremely durable. And so what that means is that they can withstand tons and tons of cycles because you're basically these valves are going to open and close with every heartbeat. And so just to give you a number to give you an idea, these valves open and close about 40 million times a year on average for an average person. And so the basically has to be designed to withstand all that loading. Okay? Another important thing is that they have to be non-thrombogenic, and so what that means is that the blood doesn't clot here. Because if you got a blood clot in the middle of your heart because of an artificial valve, that would be a really terrible thing because then that would basically cause a big heart attack and really bad stuff will happen. Right. And lastly, it has to have a large enough orifice area to let the blood flow through. And so, just like we talked about with stenotic valves, they have to be able to open up enough so that enough blood flow can come through with minimal work from the heart. And they also have to be able to close completely to not let any blood flow come back. Okay. And so there's two types of artificial valves that are currently available, and they're both great, and so they both have really good properties. And so the first type is a mechanical valve, and so that's kind of what you see in kind of this top left image right here. And so typically these are made of called pyrolytic carbon, and they kind of more closely resemble what you think of a valve, if you're working in like a piping system. Another type of valve is a biological valve, and so these can either be made of animal tissue or I think what Ronald, mentioned too, is they can also be 3D printed from some materials as well. And so these are usually mounted on some kind of frame, as you kind of see from right here. Okay. All right. Any questions on artificial valves? Okay. Okay. And so how do we actually go and replace these valves? And so it's a pretty crazy surgery, because a valve, in order to replace the valve, you first of all need to remove the one that was already there, and then put the new valve in and suture it in place. And so it used to be a really invasive surgery because, like, as you can tell, like there's a lot of really delicate things that you have to go in. You have to go in and you have to cut the valve out, you put the new valve in, and literally like stitch it to your heart in order for it to work. And so it used to be a really, really big deal to perform this kind of surgery. Um, but valve replacement surgery is not all that uncommon, and so it's a decent amount of the population has to get replacement valves at some point in their life, and so having to do open heart surgery, open chest surgery, for all these patients is usually pretty bad for these patients. And so there's been a lot of research recently into how can we perform this valve replacement without having to cut the patient up. And so, a new, well, maybe not as new anymore, but it was very new for a while. There's a surgery called transaortic valve replacement, or TAVR, and so you'll hear the word TAVR quite a bit. And what that basically refers to is a minimally invasive surgery to replace the aortic valve. And so the aortic valve is special because that's kind of the most outward facing valve, and so that's the one that connects basically your heart to the rest of your body. And so basically surgeons have developed a technique where they can perform an aortic valve replacement without having to do open heart surgery. So they basically use a catheter to go in and perform, and the surgery is done all with the catheter. And so, that's much less invasive than having to open up the patient. Okay. And so this was revolutionary when it came out because it's, a catheter type, intervention, or a catheter type surgery is much more preferred and is much more convenient for the patient than a full open surgery, when you're going to be laid out for a really long time. Okay. Yes, yeah. So TAVR is much more common now. So I think a lot of hospitals are really picking it up as the preferred method of aortic valve replacement, just because it just leads to much more quality of life for the patient. It's a lot cheaper too because you don't have to pay for the entire staff open up the patient, and it's less burden on the hospital too because the patient can go in and out. Maybe they stay overnight or something like that, but they're not in there for weeks recovering as they would for open heart surgery. Yeah. Where they insert the catheter, so they usually insert the catheter up the leg, so that's typically kind of where they do for when they need to get the catheter up into the heart. Mm-hmm. Yeah, so it's very similar to the catheter procedures that we talked about in this class. It's just now they just mount a valve at the end of the catheter. Yeah, yeah, it's actually an amazing surgery, and I kind of wish I had the opportunity to come watch these at one point because it seems really amazing. I have gone to a couple of surgeries before. I went to an open heart bypass surgery once before, and it was an experience. Seeing a dude's chest open and his heart actually beating right in front of you, it's quite an experience. I did not faint, no, but the smell is very strong. Um, and I was actually very surprised too because like I had just gone to grad school at that point, and my advisor's like, the surgeon's offering to let you go see the surgery. Why don't you go see? I guess my impression of surgery was that it was a very kind of intense thing, like doctors yelling at each other and stuff like that, like you see kind of in the TV. Patient like rolls in and the surgeon's like, oh my God, you're like, oh God, but they actually do a really good job of keeping it really relaxed. And so they're playing music, and then they're the surgeons and the nurses, they're kind of joking around with each other. Obviously they're taking their work very seriously. They're not taking it lightly. But they don't put any additional pressure on each other than what they need to. And so it was really cool to see because like all the surgeons and the nurses, it really felt like they were a really well functioning team. And they were there to support each other and keep each other's spirits up. So and the room was very bright. It wasn't a dark, scary room at all. So yeah, the only bad thing was the smell of of the person. Yeah. All right. All right, question. So how does an artificial heart recreate the ideal pressure and flow in the recipient's body if it is a program to change as we move like through exercise? Yeah, that's a really great question, and I actually don't really know enough about artificial hearts to know, I think that's a very valid concern, because every person's different, and if you put like an artificial heart in there, it should match to what the patient's demands are. And so I have no idea how they actually fit that to the individual patient. Yeah. Yeah, it's actually funny too, because I went to see the surgery back in 2016, and that was the year that the World Cup was going on, and so they had one medical intern where his only job was to bring tools and to keep everyone updated on the World Cup scores. Yeah, he just joined the hospital or something like that. So yeah, he was just bringing tools and saying, Germany won, Spain this. Yeah. Nice. Yeah. So Josh shared a video of a TAVR surgery. I'll probably check it out after the lecture. Yeah, it's an amazing thing. Okay. And so let's talk about, if you're say you're working for like Edwards Life Science and you're designing a valve, let's talk about some design considerations that you would have to make. Okay. And so, even though it would be ideal if you have your artificial valve to provide no flow obstruction at all, but just the inevitability of like having moving parts and a kind of a relatively bulky frame is that the valve has to block the flow to some degree. Okay, and so you're never going to get a fully open mechanical valve. And actually, I think the difficult thing is the frame that goes around it in order for it to attach properly to the wall. And so that's never going to be exactly the same as kind of a natural valve. Okay? And so similarly, it would be ideal if your valve would really shut off, completely, to prevent all regurgitation. But a little bit of regurgitation is almost inevitable for these kinds of mechanical valves. Especially, they actually designed some regurgitation on purpose in the gaps around the leaflets, and these are to prevent the blood from clotting. And so those are kind of very specially designed for that. And that's usually a much more important design consideration than providing full stops for sure. Okay? And so when a biotech company actually goes and designs a new valve, of course, they test it out very rigorously before they put into a human. And so, if you ever get a chance to visit Edwards Life Science in Irvine, they actually have a lot of lab setups where they actually test these valves, and they do it for I think they call it fatigue testing, where they basically load it, like millions and millions of times just to see how the valve, measures up. And they have a bunch of diagnostics to see, is the valve still closing properly, is it still opening properly, and things like that. So it's it's amazing to see, how sophisticated their equipment is. And of course, you can also evaluate these valves in CFD as well. And so, that's definitely an up and coming technology, like using some vascular to do these kinds of things. And most important, if you're designing a valve, is, the valve should be very energy efficient. And so as the blood moves through the valve, there should be a minimal loss of kinetic energy as possible. Because the more efficient your valve is, the less work that your heart has to do in order to pump blood through the valve. And that's ultimately what you want to get from your replacement valves. Okay, and so what are some complications? And so, these valves, they aren't perfect. And so I think, valves have come a really long way, but, there still might be some complications that occur. Okay. And so the primary concern with these valves, as in most devices that you're inserting into a patient, is the concern about blood clotting. And so the concern is always that you're inserting these kind of foreign materials inside your body, and sometimes you don't really know how the body's going to react to these materials, and in the worst case, your blood might kind of panic and kind of clot in that area, which is pretty much a catastrophic failure. Okay? And so a lot of times, when patients do get a replacement valve, they have to be put on blood thinners or anticoagulation therapy to minimize the risk of clotting, especially for a mechanical valve. And that's a very kind of standard thing. And so, at this point, because these valves have been kind of engineered for a while, there really isn't that much concern about structural integrity or durability anymore. We've the technology has kind of moved past that part. And a lot of the research now with artificial valves is more non-invasive, relatively non-invasive surgeries like TAVR, for valve replacement. So TAVR, that replacement works really well for the aortic valve. But if you have a valve inside your heart, like your mitral valve or your pulmonary valve that needs replacement, that still kind of requires an open heart, because the doctors haven't really developed a really standard technique to get a catheter over there to replace that valve. And so a lot of the research nowadays is, how do we implement a better surgical procedures to putting these artificial valves in. All right. So any final questions on valves? Okay. And so let's talk about pacemakers. And so pacemakers are kind of a little bit of an odd sheep in this lecture, because most of the medical devices that we've talked about have something to do with fluid mechanics in some way. Pacemakers have really nothing to do with fluid mechanics. So it's more regulating the heart's beating. Okay, because normally what triggers your heart to beat is that there's an electrical signal that comes basically from your brain down to your heart, and it basically tells it to to keep beating. And I think there's and I know very little about this, but there's a node on your heart that basically regulates that electrical signal and propagates that through the heart to make sure your heart muscles are contracting kind of in the right rhythm. Okay, but sometimes what can happen is that these electrical signals, either there might be something with your nervous system, or there might be some I call it circuitry, but it's not really circuitry, but something's wrong with the circuitry on your heart that makes these electrical signals not propagate properly. Your heart can have what's called abnormal heartbeats, and so I think the medical term for that is called arrhythmias. And that's not good, because then your heart's not working as efficiently as possible. And so pacemakers are devices that basically can help regulate these electrical signals to kind of take the place of your nervous system to help regulate your heartbeat. Okay, and so what they are, they're a lot more sophisticated in this, but they basically are just small electrical wires that go onto the outside of your heart that send little electric currents to regulate and control and stabilize your heart's rhythm. All right, question. So do MRIs have an effect on pacemakers? They have a big effect on pacemakers. And so you can't go into an MRI machine with the pacemakers. Otherwise, it's the magnets will have a strong effect on the pacemakers. Yeah. And so I think that's usually the very first question that they ask you, and they ask you about that. They ask you that probably 5 times before you get an MRI, is if you have a pacemaker, because it's you can't have that. Yeah. So I think it's not only just the metal parts, but I think the MRI, the strong magnetic field will have a strong effect on the current in the pacemaker as well. And so if your body, if your body's really relying on that electrical current from the pacemaker, you can't have something like a really strong magnet going and messing that up, because that's going to mess a lot of things up. Okay. All right. And so relative to a lot of cardiac diseases, actually abnormal heartbeats are actually relatively easy to detect, because doctors can often use their stethoscope and kind of listen to it from the outside. And so there's usually no fancy diagnostics, no medical scan that doctors need to actually do this. And so you'll see pacemakers are often very common for a lot of people, just because the rate at which doctors actually catch it and actually apply it is very high relative to some of the other diseases. Right? And so there's been some older versions of pacemakers where the electrical current was actually not implanted inside the patient, but there's actually a wire on your chest. But as you can imagine, if you're putting electrical signal through your chest constantly, this can cause some burns, because in order for that signal to reach your heart, you need a relatively high current in order to do that. And so when that current is constantly being exposed to your bare skin, that's usually not a recipe for healthy skin. That's for sure. Okay. So any questions on pacemakers? Okay. All right. And so let's talk about VADs next. And so VADs, I think, are some of the most interesting cardiovascular devices, and they're also some of the most complicated ones. And so VAD basically stands for ventricular assist device, and basically you can almost think of it like an implantable pump. And so these are implanted for patients where their heart's usually too weak or not strong enough to pump the blood that it needs to either to the rest of your body or to your lungs. And so, since your heart is essentially a pump, for those kinds of patients, doctors basically said, why don't we just put in another pump inside the person's body and, have that pump actually work for them as well. And so these are called VADs, or ventricular assist devices. Okay. Right. And so most commonly, you'll see these VAD devices used to support your systemic circulation. And so, in other words, they're supporting the left side of your heart, because your left ventricle is basically responsible for pumping blood to the rest of your body. And so the most common type of VADs are called left ventricular assist devices, or LVADs. And so you'll hear the word LVADs quite a bit. Okay. And so these are implanted for a number of reasons. Usually it's not a permanent fix. And so usually, people don't implant a VAD and expect you to live with that for many, many years of your life. But it's usually kind of a stopgap measure for patients who are awaiting a heart transplant. And so, appropriate hearts for heart transplants usually don't come up every day. And so usually a patient will have to wait, a while before a suitable heart is available for them. And so a VAD is usually implanted in these patients to kind of give them a stopgap measure so that, they get appropriate circulation until they can get, a heart available for them. Okay. And so, since this is, a device that goes inside your body, it's a very invasive surgery. And so, it actually exists outside your blood vessels too, because it's a device that goes kind of exterior to that. And so open heart surgery is kind of unavoidable in these. Open heart surgery always carries its own risk, but for a lot of these patients, it's really the only option that they have. Otherwise, their heart's really not strong enough on their own. Okay. All right, and so let's talk about some risks and complications. A lot of the risks for VADs is very similar to other devices. Because you have blood that's going through this foreign device, and in this case, it's being pumped, which is a very active process. And so the primary concern with these is blood clotting. And I would say the concern for blood clotting in a VAD is much, much higher than something in a valve, because the VAD is actually an active device. And so it's actually going to be actively pumping the blood. And so there's a lot of moving parts. It's going to be, squishing the blood. It's going to be pushing the blood through. And so, a lot of times the blood's not going to react, fondly to that. Because the blood's not really used to, this metallic or oftentimes, or whatever material type of device pumping the blood through their body, right? And oftentimes these VADs have pretty narrow channels for the blood to flow through as well, right? And so, just like for artificial valves, if you end up getting a VAD, some kind of blood thinner or anticoagulation therapy is basically required, because otherwise, the risk of blood clotting is really, really high. And some other risks include, because these devices have to be powered from the outside, there's actually wires that actually, run from, the inside of your body out. And so there's risks of bleeding and also of infection for, the entry points for the wires as well. Yeah. Okay. Any questions on VADs? Okay. Okay, and so let's talk just very briefly about regulation of medical devices. And so, just like any kind of device, medical devices are regulated by the government, and they're actually subject to even more stringent regulation, because they're classified under what's called safety critical devices. And so what that means is that if a medical device fails, like say like an artificial valve fails or a VAD fails, this can lead to really significant harm or death to a human being. And so that's a really serious thing. And so the government really heavily regulates these kinds of devices. And so in the U.S., the agency that's responsible for regulating medical devices is the FDA. And so anytime you develop a new device, you have to go through the FDA, in order to make it, in order to sell it on the market. And so, if you work at any kind of biomedical company, you'll be very kind of familiar with this. And so any kind of new device, or even like a modification to an existing device, it has to go through a really rigorous approval process to basically show that, before you actually expose this to the common public, that, all the risks and all the complications are known and minimized to the best of your ability. Okay. But it's important to know that as with any engineering device, not just medical devices, it's impossible to eliminate all the risks. And so if you're sticking like a pump inside a person's body, there's always going to be some risk associated with that. And so, the goal is never to eliminate all the risks. And the FDA wouldn't ask you to do that. But it's important to know, it's important to, know, first of all, know all the risks that are involved and to minimize them as much as possible. Because, these devices are having a direct impact on people's lives. Most times it's positive because, these devices are in for patients, that have some kind of, serious disease, but you don't want these devices to go wrong and, to really harm the person. Okay, and so I can't scroll anymore, so it looks like that's the end of that those lecture slides. And so any questions before we move on to CFT? So that is what's holding back a lot of these additively manufacturing parts. Biocompatibility is huge too. Yes, yeah. So it's it's a long process, and like if you work in the industry or you're intern there, the amount of time it actually takes to go from the development of a new device to the market can often take years sometimes, because it's the process is really rigorous, and you have to show a lot of things in order to make sure that it's safe. So it's a process, and so the lawyers at these biotech companies really earn their money, because it's a tough process to go through regulation. Yeah. Okay. And so that's everything I wanted to say about cardiovascular diseases and medical devices. So now let's talk about now let's change gears almost completely, and let's talk about CFD. Okay. All right, and so this is really exciting for me because I haven't really talked about CFD in this detail, or really want to workshop like this ever since I started working here. So this is kind of like a test run, because I do want to introduce more CFD into the curriculum, and you guys are kind of the guinea pigs for, how well the CFD do for for Cal State Fullerton students. And so, throughout this whole process, I'm, definitely don't be afraid to give me feedback on this stuff. If things don't make sense or if things are confusing to you, definitely let me know. Because this is one of those things where, like, I've been running CFD for a long time, and there's some things that I take for granted, or things that might seem obvious to me, that might not be obvious to someone who's never run this before. So please, please keep me updated on, if something doesn't make sense, or, if something's confusing, because, I really want to make this good. Yeah. And so actually my goal is to actually develop a grad level CFD course for Cal State Fullerton. Yeah. Probably not next semester. And so I'll probably develop it over summer. And so I'll probably put it up for approval sometime in the fall semester. And so I'm hoping by next spring I'll have a CFD class available. Yeah. Mm-hmm. Okay, and so let's talk about CFD, right? And so here are all the learning objectives. And so basically, this is just going to be a first introduction to CFD. And so just to basically, we're just going to describe what it is and what are some common applications. And most importantly, I want to talk about just the general steps to running a CFD simulation. Okay? And so if some of you guys are in some of my other classes, like finite elements or computational heat transfer, you'll definitely see some overlaps with that, because a lot of these steps are the same. But I wanted to really start from scratch, for those of you who have never run a computational simulation before. Yeah. I took this class for the CFD. Unfortunately, we're just going to cover just kind of the practical use of CFD, so we won't be covering any of the theory, because that's a whole class in itself. And actually, Vascular actually uses the finite element method for CFD. And probably we can talk offline about why that is. But actually, the typical method for a lot of CFD codes, I think Star CCM uses this, is finite volumes. Yeah. So finite volumes is definitely more common for CFD, but Vascular actually uses finite elements for that. Mm-hmm. Okay, and so what is CFD? So CFD stands for Computational Fluid Dynamics. And so I often forget this. I actually forget this fact a lot. And so I say CFD, and then people always ask me, what does CFD stand for? And so it stands for computational fluids. Okay. And basically what it is using computers or any other kind of high performance computing to simulate fluid flow. Okay. And so in this picture, what you see here is basically we're simulating the flow of air around an elephant. Okay. Why people are simulating flow around an elephant, I have no idea, but it produced a very nice picture that I can use in this presentation. Okay. And so the way that CFD codes do this is that they take the equations for fluid flow, primarily the conservation of mass and momentum, and they solve this computationally. Okay. And so, the conservation of mass and momentum for a fluid, that's, the Navier-Stokes equations. And so normally, this is impossible to do by hand. But if you formulate those equations and you kind of discretize them in a certain way, you can have a computer solve these in much more, in a much more easy, much more easily than if you solve them by hand. Okay. And basically what we're doing is we're basically leveraging the computer's ability to do a ton of calculations, really quickly. And we're going to use that to basically simulate complex fluid patterns and complex geometries, right? And so, we're going to be looking at situations with CFD that would be impossible to do by hand. And it would be really hard to actually do an experiment for too. And so, CFD has a really, it's at this point, it's really carved out. It's a really strong niche in the engineering community. Someone did one for a Bulbasaur. Yeah. People have done CFD around a lot of really interesting, shapes. Bulbasaur is definitely very blunt. He's not a streamlined boy at all. All right, and so CFD. I talk about CFD as kind of a general method because there's a lot of different codes that actually implement it. And so some codes that you might have heard of are ANSYS. And so ANSYS actually does finite elements for fluids, actually very similar to Vascular. And so ANSYS, works well if you can get your hands on the commercial license. Okay. A very popular open source one that you can use for free is OpenFoam. And so I've actually got some questions from students in the past on how to use OpenFoam. And so I'm actually, trying to, well, first of all, I have to teach myself how to use OpenFoam. And I'm going to see if I can incorporate into some of my other classes like 417. Okay. There's Star CCM, which I think, Ronald mentioned at the beginning of class today. And so that's very popular for aerospace applications. And of course, there's also some vascular. Yeah. Oh yeah, boomerangs. Yeah, that would actually be pretty cool. I've never seen a CFD simulation of a boomerang before. Yeah. And so usually, what you'll see is that, there's usually not one CFD software to rule them all. And so usually a CFD software is usually specialized in one particular thing. At least most of the useful ones are. So we'll be using some vascular in this class. And so that's very specialized for blood flow. And then Star CCM is very specialized for doing, airflow applications. And so if you want to run CFD, you really have to look at, what's the application that you're using and what's the most appropriate software to use for it. Because every software is kind of good at different things. All right, and so let's talk about some applications. So what is CFD used for? And so probably the most common application that you'll see, especially for mechanical engineers, is in the aerospace industry, right? And so this is for simulating flow over airplanes, flow over rockets, propulsion. If you work in propulsion, CFD is a big part of that as well. And so just aerospace, just in general, which just works with a ton of fluids. And so CFD is huge in that. Okay. CFD is also used in weather modeling and prediction. And so what you're actually seeing right here is actually the airflow over some metropolitan area. I don't remember which one this is, but you can see, it's they're basically simulating the wind pattern around all these tall buildings here. Okay. It's also used in industrial manufacturing, especially the ones that have to have any kind of extrusion or any kind of anything where there's fluid flow. Biomedical, of course, that's what we're working on this class. HVAC, which stands for heating, ventilation, and air conditioning, and so any kind of AC or heating system in your home, that usually involves airflow in a home, and so that obviously you can simulate with CFD. Okay. Thermal engineering, and so things like heat exchangers, electronics cooling, you can simulate with CFD. And automotive applications as well, and so the flow of coolant in an engine or the flow of fuel. There a lot of those can be simulated with CFD as well, and I think that's where this image came from on the bottom right. All right, so any questions about CFD so far? Okay. All right, and so how do we actually run a CFD simulation? And so even though I just finished talking about there's so many different softwares, but no matter what software that you're in, the general steps to running a CFD simulation are relatively the same. Of course, there's small differences depending on the software, but I've kind of broken it down into these 7 steps that you need to do. Okay, and so we'll be going over each of these 7 steps in detail, and what do I mean by these? And what you'll see is that no matter if you're using some vascular, you're using OpenFoam, you're using Star CCM, you're going to have to go through each of these steps in order to run your simulation. Okay. All right, and so let's go to the first step. And so the first step is simply defining the problem. And so this is actually even before you open up your software and before you actually load up a CAD file or anything like that. You have to define what kind of engineering problem or what kind of engineering situation you want to simulate with CFD. Okay. And so this is kind of just a generic image that I pulled from Google, but you really have to ask yourself, maybe not these questions. So you don't have to yourself who is CFD, where is CFD, what is CFD, but these are the kind of questions that you should ask yourself, right? And so you should ask yourself, what's the physical domain, or in other words, what's the geometry for your analysis, right? And so basically, what type of geometry you're going to be simulating flow through. And so for our class, this would be blood vessels, right? And so the blood vessels, these are going to define the domain. These are going to define the geometry for your analysis, right? And so you have to establish that first and foremost. And, a lot of these questions might seem, very simple and straightforward, but, you would be surprised at, the amount of, simulations that can go wrong, and the amount of waste resources that people do just because they don't ask themselves these really basic questions about their analysis. Okay? And so second question, so what kind of physics are relevant for my problem? And so if you're running CFD, fluid mechanics, obviously is something that's going to be very important. And so that's a big part of the physics. But if you're running something like a combustion simulation or some kind of thermal simulation, then you also have to include things like heat transfer, things like chemical reactions, right? And so you have to really define what type of physics in addition to fluids will be relevant for this problem, right? Or for our case, if it's just fluids, then you have to kind of define that too. And so you can say, in this case, I'm only interested in the fluid mechanics. And so that's an important distinction that you have to make as well. Okay. All right. And so the third question is, what equations govern the physics of my problem? Okay. And so this kind of goes along with the second question there. And so if you're solving like some kind of thermal heat transfer kind of situation with fluids, and so, obviously the heat equation is going to be important there. Okay. If you're solving like another common situation is like mass transport, right? And so, one situation I see people simulate often in cardiovascular simulations is, if we inject a drug into this person's bloodstream, how does that blood, distribute throughout the person's body? Okay. And so in that case, you need the equations for mass transport as well. Okay. And you need to make sure that your solver is equipped for that. Right. So fourth question is, what information do I want to get out of this analysis? And so this is really important because you have to define, what are the outputs that you expect to get? And so do you need pressure information? Do you need wall shear stress information? Do you need information on the flow rates? Do you need thermal information, right? And so, you have to define, what information do you want to get out, and how do you actually obtain that information from the simulation, okay? And then last question, and most important, you have to kind of visualize, what do the results kind of look like, right? And so you should never go into a simulation blind. And so you should, anytime you run a simulation, you have this geometry and you apply these boundary conditions, you should have some idea of what the results look like. Of course, you shouldn't have, you probably won't know the exact numbers, and so you won't know exactly what the velocity is here, what's going to be at this point. But you should generally say that, the flow should go this way, right? And so the pressure should drop when I go through this vessel. The wall shear stress should be high in this region, right? And so this is really important because I think the trap that a lot of people get into when they run simulations is that, they kind of, run their simulation and they kind of go in blind, and then just whatever the simulation pops out, they kind of take that as reality. And so that's absolutely false. And so, ideally you would want your simulation to reflect reality, but there's a lot of things that can go wrong when setting up a simulation. And so you want to really make sure that you have some idea of what your results should look like so that you can perform sanity checks at the end. Yeah. So Ronald makes a good point too. And so there's a lot of flow quantities associated with circulation and vorticity as well. Yeah, definitely for aerospace too. Aerospace is definitely interested in vorticity. Yeah. So I can't stress that last point enough, because I've seen, a lot of people, basically run their simulations and they take that as like word of God or something like that. And so, they'll run their simulation in Simvascular, or they'll run a simulation in ANSYS, or even in MATLAB, and they said, this is what's going to happen. And, a lot of times, especially if you're working in an engineering company, your managers or your fellow engineers, they're going to take your simulation results and they're going to make decisions on based on your results, right? And so they're going to fabricate things a certain way. They're going to order materials. They're going to sell, a certain product based on what your simulation is going to say. And so you want to make sure that your simulation is accurate as possible. And so, you have to really ask yourself the questions of, does this simulation make sense to me? Because if it doesn't, it's likely that you set up something wrong in the parameters somewhere. And so you have to go back and fix it. Okay. All right. And so, it's even, I would even go as far as to say that, it's really useful to even just draw a quick picture of what you expect the flow to look like, right? And so if you have, like, say, for instance, that you have flow in a pipe, you can draw a picture of a pipe and you can have blood flow going through it, right? And so anything that basically helps you visualize, what the results should look like so that you can perform sanity checks at the end, I would definitely encourage you to do that, especially when you're running your first few simulations. And so because what you'll see, when we do our workshop next week, that there's a lot of parameters that you can set for a simulation. It's almost overwhelming, the amount of options that you can have. And there's a lot of wrong ways that you can set up a CFD simulation. And so, by having sanity checks at the end, you can kind of stop yourself from reporting some erroneous results. Okay. And so, defining the problem, this is a step that I think a lot of people skip, but I think it's probably the most important one because, you have to really know what you want to simulate before you actually go in and simulate it. Okay. All right. Any questions on this? Okay. All right, and so the next step that we'll go over is modeling the geometry, okay? And so in order to run a CFD simulation, you have to have basically a computer model of your geometry that you want to run your simulation in, okay? And so in a lot of cases, this takes the form of some kind of CAD file. And so oftentimes people use SolidWorks for this. But, because we're in this class, we're using SimVascular, obviously our geometry is going to come from, the blood vessels that we model in SimVascular, okay? But you have to get your geometry from somewhere. Okay? And so, and some important notes specifically for CFD, because a lot of people make this mistake too, that when you create the geometry for your simulation, you have to make a model of the region where the fluid will actually flow. Okay. And so what I mean by that is that usually when people make CAD models, in SolidWorks, they usually model the solid parts of the geometry, right? And so let's say that you have flow in a pipe. And so if you make a CAD model for a pipe, or you ask, some engineering student to make a CAD model for a pipe, they'll probably make some hollow cylinder like this, right? And so this might be like a PVC pipe or an iron pipe or something like that. But something like this won't work for CFD because, the region where the fluid flows right now is just empty space. And so there's nothing there. And so what you need to do instead is you need to kind of fill the empty space with the model. And so you actually need to make like a solid geometry of the place where the fluid's actually going to flow. Okay. And so in this simple example right here, basically you want the one on the bottom, which is basically has a solid cylinder where the fluid is going to be expected to flow. And so the one on the top won't work at all because the top is modeling kind of the solid domain, but the bottom is actually modeling the fluid domain. So that's where the fluid's going to flow. Okay. Right. And so, since we're working in SimVascular, you don't have to worry about this at all because SimVascular knows that you're going to run a CFD simulation anyway. And so it models kind of the blood vessels kind of one solid kind of block. And then, you can simulate fluid flow from there. But if you're running CFD from another software, this is a really important point to remember, so that you don't do something like this, because otherwise your simulation is not going to work. Okay. All right. Any questions on this? Okay. All right. So the next step is meshing, and so this part is always kind of fun to do, depending on how on if it worked for the first time or not, right? But the next step, in order to actually run a simulation, you have to take your geometry and actually break it up into a bunch of simpler shapes. Okay. And so the reason we do this is that oftentimes, when you're producing like a CAD geometry, that's often too complex for a computer to just compute fluid flow on there directly. And so you have to break this up into a lot of simpler shapes so that the computer can actually handle that. Okay. All right, question. So verification of CFD results, would I use Navier-Stokes or Bernoulli or something like that, depending on the situation? Yeah, so actually verification is a really important task. And so for verification, I would actually use experimental measurements if they're available. And so if you have, some kind of experimental measurements or some kind of observations, in a similar geometry, if you can get your CFD simulation to match those, then that's usually good for validation. Yeah. But for testing your code, oftentimes people will simulate. They'll run their CFD on like a known geometry, and so they'll run it on like a simple pipe, and you can solve for pipe flow pretty easily by hand using Navier-Stokes, and so you can verify between your simulation results and your hand calculations as well. And so that's another way that people verify the results. All right, and so this process of breaking up a geometry into simpler shapes, this is called meshing. Because visually it looks like we're kind of putting like a wire mesh on top of our geometry. Okay. And so the shapes that the software will break your geometry into are usually of two varieties. And so the first variety are called tetrahedrals. And so tetrahedrals is basically a fancy name for a four-sided pyramid. Okay. And another shape that is often used is hexahedrals. And this is a really fancy name for basically just a box. And so it's basically a six-sided box, with lines and edges and things like that. Okay. For Simvascular, we're going to be just doing tetrahedrals, and so you don't have a choice, and so you're going to use tetrahedrals, and you're going to like it. But for other softwares like ANSYS, you have other options for hexahedrals as well. Okay. All right. And so when you're meshing, the primary thing to look out for is the number of elements or nodes that you get in your mesh. Okay. And so the higher number of elements that you have, the more computationally expensive your simulation is going to be, okay? And what I mean by that is, the more nodes and elements that you have, it's going to require more time and more computing power in order to run your simulation, just because there's just a lot more calculations for your computer to do, okay? But the higher number of elements also means that you get greater accuracy as well. And so it's a balance that you have to make. And so you want your simulation to be accurate enough to have, useful results, but you don't want to mesh, you don't want your mesh to be so fine that you're running your simulation for weeks and months. Okay. And so you usually want to find a sweet spot for your mesh. And so for this class, I would say that, you guys can probably do your projects with a mesh of about, I would say 400 to 500,000 elements. And so that's a number that you should be shooting for your meshes. And, and I'll remind you of this, as we get to that part of the project as well. Okay. And one analogy that I like to make about meshing is think about, the resolution of the computer image, right? And so typically, if you're looking at some crappy JPEG from taken by a potato back in 1997, you have a very pixelated image because there's not very many pixels that are in that image, right? You compare that to a very high def, like 4K image today, the 4K image is going to look much more clear because it has a lot more pixels, right? The difference is that, the more pixels that you have in your image, the more memory it's going to take up on your hard drive, right? And so a 4K image might take up, a few megabytes in your hard drive, but some potato JPEG image from the 90s might take up a few kilobytes or something like that, okay? And so it's the same thing for meshing too. And so the more meshing elements that you have, the more refined and more accurate your solution is going to be, but it's just going to take a lot more work and a lot more time in order for you to get a solution on that refined mesh. Okay. All right. Any questions on meshing? Okay. All right. And so the next thing that you have to do is you have to apply boundary conditions. Okay. Because now that the geometry is meshed and the computer knows that it's solving Navier-Stokes, the computer can actually take it from here and actually solve for all the solution values basically on the interior of the mesh. Okay? But what the computer doesn't know what to do with is what to do at the extremities of your mesh. Okay, or in other words, the boundaries. And so in order for you to actually run a successful simulation, you have to specify, what kinds of conditions that you want on these boundary elements. And so these are known as boundary conditions. Questions. So you said we're limited to tetrahedrals. Yeah. So the mesher inside Simvascular is limited to just tetrahedrals. Yeah. And the reason for that is because cardiovascular geometries end up being very complicated. It's really difficult to get a hexahedral mesh inside like a blood vessel that kind of does a lot of twists and turns. And so, we're kind of limited to tets in that case. Yeah. Mm-hmm. All right. And so the reason we need boundary conditions is, kind of think back to your previous math classes where you solve the differential equation by hand, right? And so when you solve differential equations by hand, not only did you have to find the general solution, But you had to apply things like boundary conditions and initial conditions to fully specify the solution. Right? And so for CFD, it's the same way. And so you not only need the Navier-Stokes equations and you not only need your mesh, but you need also the boundary conditions in order to fully specify that solution. Okay. And so there's two types of boundary conditions that we're going to specify, or two categories, I would say. And so one type of boundary condition is going to be at the inlets and outlets, okay? And another type is going to be at the walls. And so we're going to go over that now, okay? All right, so let's talk about inlet and outlet boundary conditions. And so I kind of categorize these in the same because these are boundary conditions that specify, regions where the flow is going to pass through the surface, okay? And so if you look at kind of this inlet and this outlet here, you can see the fluid is passing through that surface, okay? And so that's why I kind of classify these as kind of the same. And so think of basically the inlet area and the outlet area of like a pipe, okay? And so for some vascular simulations, you'll see that the terminology that some vascular uses for this is called caps. And so the caps of your model basically denote the inlets and outlets that you need to apply the inlets and outlet. And so for the inlets and outlet boundary conditions, there's basically two types that we can run. And so the first type of boundary condition is called a flow boundary condition. So another name for this is Dirichlet. Okay. And what these do is they specify the amount of flow or the velocities at the cap, used sometimes as a function of time. Okay. And flow boundary conditions are typically used as inlet boundary conditions. And so that's what we're going to do in SimVascular. And so in SimVascular, we're basically going to specify, a fixed amount of flow at the inlet of our model. Okay. All right. And so the other type of boundary condition that we could specify is a pressure boundary condition. Okay. Kind of the fancy scientific name for this is a Neumann boundary condition. And so these specify the pressure or the pressure waveforms at a cap. Okay. And so these are typically used for outlet boundary conditions. Okay. And so typically, for CFD simulations, you have flow at the inlet and then pressure at the outlet. And the reason for this, if you're curious about this, the reason for that is it has to do with the kind of the numerics and kind of the numerical stability of it, And so, if we had kind of 4 weeks to go into CFD theory, I can kind of explain that. But just from a practical standpoint, just know that if you're running a CFD simulation, you use flow at the inlets and pressure at the outlets, and that usually leads to the best results. Okay? And so for SimVascular, we're actually going to specify a special type of pressure boundary condition called a resistance boundary. The term resistance should ring some bells because it's actually very similar to the LPM concept of resistance that we went over, a couple of weeks ago. And so, SimVascular actually uses this concept of resistance to actually apply a much more realistic type of boundary condition specifically for a cardiovascular simulation. And so, what the resistance basically will do is that it'll apply a pressure boundary condition that's proportional to the amount of flow and proportional to the amount of resistance that you assign at that outlet. Okay. Yeah. It's you can kind of think of a flow boundary condition as kind of like a fixed support as well. Yeah. So for some of you who are coming in from like finite elements or from 417, there's some terminology that's here too. But basically, the reason I use that same terminology here is because Dirichlet boundary conditions are used to specify conditions on the primary solution variables. And so like when you're solving for Navier-Stokes, the primary solution variables are the velocities. And so, when you supply a condition on the velocities, then that's a Dirichlet boundary condition. But for structural simulations, what you're solving for is the displacements. And so when you're directly specifying the displacements, then that's the same thing as the Dirichlet boundary conditions. Yeah. So Dirichlet and Neumann are more computational terms than anything. So it doesn't really it's not defined by just displacement or velocity or things like that. It really depends on the type of equation that you're solving. Yeah, I realize the terminology can be confusing if you're coming from 417 or 410. Yeah. And so, boundary conditions are really important. And so these are the things that people typically, kind of mess up in their simulations, that they don't set these up properly. Okay. And so that's the inlet and outlet boundary conditions. Now let's go over the wall boundary conditions. And so wall boundary conditions are basically specify the solution of the behavior of the solution where the flow is not supposed to pass through. Okay. And so these, for synovascular, these will basically be the lateral surface of the blood vessels. Okay. And so by far the most common wall boundary condition that you'll see in practice is called the no-slip boundary condition. And so what that means is that the velocity basically has to go to zero at the walls. Okay. And in fact, if the walls are rigid, that means the velocity has to go basically to zero. Okay. And for most of your projects, that's what you're going to be running. And so you're going to be running a rigid wall simulation, just because it's computationally kind of the easiest thing to do. Okay? But we did just get done talking about how deformable walls are extremely important for cardiovascular flow because of things like the wave propagation phenomenon and things like that. Okay, and so you can run simulations with the deformable wall, and synovascular is actually equipped to do that. And you can certainly do this for your project. I'd be happy to kind of walk you through that, but it's not required because it does take quite a bit of setup to do in order to run a deformable wall simulation. But I did want to let you know that it's there. It's possible to, but it's not going to be required for your project. Okay. Okay. So any questions on the boundary conditions? Okay. Okay, and so the next step in the CFD framework is to specify your solver parameters. Okay, and so I put solver parameter. I should have put this in quotes because solver parameters kind of encompasses a lot of different things. Okay, because now that we've specified the mesh and we specified the equations and we specified the boundary conditions, technically we're ready to go, and so we're ready to start the simulation. But before we do that, there's some additional parameters that you can run or that you could set before the simulation is run. Okay. All right. And so the first thing that you can set is first of all is just the fluid properties, and so things like the density of the fluid and the viscosity of the fluid, these must be set. Okay. And so we have to set these to the density and viscosity of blood. Okay. And so the next property that you have to assign is the time step size. And so I think this is the thing that confuses a lot of people. Okay. And so when we run our CFD simulation or when we run any computational simulation, we're going to solve the simulation as a function of time. Right? And the way that the computer is going to solve this is it's going to solve it one time step at a time. Right? And the time in between each of those time steps, that's defined by your time step size. Okay. And so I think kind of the easiest analogy that I can think of is, think of like a video, right? Or think of like any kind of movie or things like that, right? And so a movie or a video is not really, an action thing playing in front of you. It's a bunch of still frames that are being played really, really fast, right? And so, if you're looking at things like movies, or you think of things like a monitor, things like that, you'll usually come across something called the frames per second, right? And so that's basically the amount of frames that the movie puts out per second to give you the illusion of motion, right? And so that's kind of how movies work, right? And so the time step size basically is kind of like that. And so for simulations, we're basically going to be solving the simulation one frame at a time. And the time step size basically defines how much time is in between each in between each frame. Okay, right. And so, like, say for instance, you have a video that plays 30 frames per second, and so the amount of time in between each of those frames is going to be 1/30, right? Okay. All right. And so typically, smaller time step sizes usually result in higher accuracy, and so just like for movies. And so the less time you have in between frames in your video, it's going to lead to a much more fluid, much more clear picture, right? And so same thing for simulations. And so the less time that you put in between each time step, it leads to a more accurate and more fluid type of simulation, but it also results in more cost, right? And so let's say that you want to simulate something for 16 seconds. And if you make your time step size 0.1, it's going to take 160 time steps in order to reach the conclusion. But then if you make your time step 0.01, then it's going to take 1,600 time steps in order to reach, the total time there. And so, that's something to kind of keep in mind. Okay? And so the next parameter here is the number of time steps. And so that defines, how many time steps you're going to resolve your simulation for. Okay. And so one thing that you're going to have to do is you're going to take the time step size and you're going to multiply it by the number of time steps, and that's going to give you basically the amount of simulated time, or the amount of time that you're going to simulate. Okay. All right, and so the next thing that you have to set is you have to set how often you want to save your results, okay? And so usually it's not practically feasible to save your results every single time step, because if you're running your simulation for like 5,000 time steps, you don't want to have 5,000 output files for you to, for you to look at. And so usually, what happens is that, the simulation only saves about every 20 time steps, just to kind of save you on the memory and save you from writing out so many files. Okay. And so this is actually, pretty important because you don't want to save too often. Okay. Okay. And the last set of parameters that I'll talk about are parameters that are associated with the linear solver. Okay. And so for this class, we don't really have enough time to talk about, the linear solvers and kind of the guts and the nuts and bolts for CFD solvers. But you could kind of think of these linear solver parameters as controlling on how accurate and how hard you want your simulation to work for accuracy. Okay. And so for this class, we're not going to have to adjust these. So I'll give you kind of a set of these parameters that should work for most of your simulations. But if you're having things like you're having issues with accuracy or stability, you might want to look at these and explore these further. Okay. But for this class, you don't really have to worry too much about what these parameters do. But I just want to make you aware that most solvers will give you the option to modify these parameters, and I want to let you know what they do. Okay. All right. Any questions on this page? Okay. All right. And so now we're at the step, which is the most exciting part, which is to actually run the simulation. And so it's simultaneously the most exciting and also the most boring part, because when you run the simulation, basically what you're going to do is you're going to upload your files to the supercomputer, and then you're just going to let it run, and then you're going to wait until it's done. And so it might seem like the coolest part, running the simulation, but a lot of times the simulations just take time. And so the amount of time it takes for your simulation can range anything from like a matter of minutes to hours or to even days. Okay. And so these simulations, we're going to be using a supercomputer for this, but that's not to say your simulations, they can't run on your personal machines. And so you absolutely can run your simulations on your personal machines. It just will take like a really, really, really long time. Yeah, and so your laptop might die. Yeah, so we're not going to be running the simulation on your own machines, because that would probably cause a lot of your computers to die. Okay, because a lot of your personal machine, I mean, depending on how strong your computer is, you're probably limited to something like 4 processors, at the most. Maybe your computer only has a dual core or things like that. But if you run on a supercomputer, these supercomputers are systems that are tailor-made and designed for running really, really heavy simulations. And so you can dedicate like dozens or hundreds of processors to a single task, right? And so I think for most of your simulations, probably I think what'll be good is to run your simulation on 48 processors at the same time, right? And so you can think of that as like 48 computers running your simulation at the same time. It's going to run that much faster. Okay, right? And depending on the nature of your simulation, even on a supercomputer, simulation can run for several weeks at a time. And so the amount of scale for these is astonishing. Yeah. If it can run Cyberpunk, it can run anything. You'll see a lot of these simulations are actually heavier than these games, just because the amount of calculations that they have to run. Yeah. It's just the sheer volume of arithmetic that has to be done for CFD is just way beyond any kind of computer game can imagine. Yeah. And I will say that this image you have here. So if you search up like supercomputer or some supercomputing cluster, you'll see a lot of images like this. This is not real, and so this is like a Hollywood interpretation of what a supercomputer is. So a real supercomputer will not be this clean. It won't be lit up this nicely, and so it's this is kind of a Hollywood interpretation of that of what a supercomputer is. Since we're almost out of time, I'll tell just kind of a quick story. So, and we'll finish up the lecture slides later. But I remember when I watched The Martian, the movie, Donald Glover's character, he played like a computer nerd geek kind of guy. And at one point, like he ran a simulation and he connected his laptop to the supercomputer and he ran a simulation, and the supercomputer's like, your simulation is correct, Don Glover, congratulations. And so it's not like that at all. It's not glamorous like that at all. So a lot of times, when you're running simulations, you're sitting, in your office, you're sitting, in your home or something like that. And the computer most definitely will not compliment you on your work. And so it won't say that you're correct. It won't say nice things to you. More often than not, the computer will complain. And it's like, you set up the simulation wrong. You got an error here, things like that. And so computers are not as nice as what Hollywood makes them out to be. They just complain a lot, and they just kind of get on your nerves. Yeah. All right. And so, that's all we got time for today. And so it's 6:45. And so next Tuesday, what we'll do is I'll finish up these slides. And so there's only a few more. And then we'll have our workshop on how to actually set up a CFD simulation in SimVascular. Okay? And so we'll run through this entire process of defining the problem, getting the geometry, meshing, boundary conditions, parameters, and I'll show you how to connect to the SimVascular supercomputing gateway, which is the resource you're going to use for these simulations as well. Okay. And so look forward to that. And so, we'll be running our CFD simulations next week. Okay. All right. So thank you guys for tuning in today. Hope you guys all have a good weekend, and I'll see you guys next week. Thanks, guys.